Hello all, welcome back to my YouTube channel all about VLSI. In this particular video, let us try to understand about PCI, Peripheral Component Interconnect. And in our previous videos, we have discussed in great detail about what do you mean by ISA and what do you mean by EISA. And also we have discussed about disadvantages of ISA and EISA. Now, let us try to understand what do you mean by PCA. And what are we going to cover in this particular session is we are going to first of all see about history and origins of PCA, why PCA was created and how Intel and PCA SAG was grew and adopted, and we are going to discuss about architecture and working of our PCI. And we are basically going to compare ISA versus EISA and PCI. And we are going to look into the advantages and disadvantages of PCI. And next, we are going to look into the new terminologies which was introduced into PCI and the evaluation of PCI, like what is after PCI. So that is this particular session's agenda. Now, in our previous sessions, we have seen what was the issues which we were facing with ISA and EISA. The major issue was we were basically having the issue of tying to the same clock. So both bus and the processor are tied to a same clock. So bus speed scaled with and was limited by the processor's own bus, capping the performance. And the second problem was manual configuration, like interrupts and EMA channels and input output addresses were basically allocated via jumpers or dip switches. And that was basically having manual configuration. You need to manually check it out. And that we have already discussed in our previous session. And we were having low bandwidth in the case of my ISA and weak bus mastering. I was having only a central bus. No particular peripheral can act as a bus master. Only a dedicated DMA master can act as a bus master in the case of my ISA and EISA. This was a problems before PCA. Now, so coming to the history of PCI in 1990s to 1991, Intel begins developing PCI internally, and in 1992, PCI 1.0 released it, where it is basically open licensed and free specifications was given. And in 1993, PCA 2.0, where connector and card specific finalized, and in 1995, PCA 2.1 was given with 66 megahertz support, and mainstream rollout begins. And in 1998 to 99, mini PCI and PCI X arrive, and PCI 2.2 adds power management. And in 2003 to 2004, PCI Express begins replacing conventional PCI. And we are also going to learn why PCI was replaced with PCIe and what was the problems with PCI also in our upcoming sessions. And in this particular session, let's focus upon what do you mean by PCI and what was the advantages of PCI, which replaced ISA, and EISA, right? Now, coming to architecture of my PCI, so I'm going to have a data width of 32 bits and 64 bits, it's optional. And bus clock, I'm going to have 33 megahertz. And in PCI 2.1, I'm going to have 66 megahertz. And maximum throughput is 133 megabits per second to 533 MBs. And addressing was, this is a major important point over here, addressing. So addressing, we can use multiplexed address and data lines. So same bus lines can be acting as a address lines and same bus lines can be acting as a data lines. So this was multiplexing. And bus mastering, this is also a very good feature which was added in PCA bus. Whereas in the case of ISA or EISA, the same bus, we are going to have dedicated buses for data as well as address. But in the case of my PCI, a same bus can be acting as an address bus, or it can be acting as a data bus. And configuration. So basically, in the case of my PCI, I'm going to have plug and play configuration via a particular concept known as configuration space. And I'm going to have slots per segment. So slots per segment has also increased in the case of my PCI. So this is the architecture of my PCA. And coming to the working principles, as I've said you previously, that I'm going to have multiplexed bus and burst transfers. So in the case of ISA or EISA, I was not having the feature of burst transfers, but in the case of my PCI, I'm going to have a concept of burst transfers, where I'm going to have multiplexed address and data lines. So as I've said you previously, that the same physical pins carry the memory address in one clock phase, then in the next, then the data in the next. and we are going to allocate very few pins and smaller connected than EISA, and we are going to have more bandwidth. And we are also going to have burst transfers. If you have studied about AHP protocol, you might have heard about this particular burst transfers, where one address phase can be followed by many consecutive data phases, and it is basically dramatically boosting throughput for larger tasks like disk input output or video frames. And this is a very best feature which was added in PCA bus. So this is what. So same pins can basically do two jobs. One is address phase and another is data phase. And it is also going to repeat for my burst operations. And also the plug and play via configuration space. I'm going to have something known as configuration space. Every particular device which was inserted in the slot is going to be allocated with something known as configuration space. And it is basically 256 byte configuration space where I'm going to have vendor ID and device ID for basically for identifying my card, what was inserted, and the class code, like what kind of device it is, and something known as base address. So I'm going to have when you're dealing with memory devices, you are going to have something known as base address. So that was also being configured in this. And interrupt line, what kind of interrupt line, what is the interrupt which was provided to that particular card. So every PCI device implements this particular space and letting firmware and OS read it identity and needs automatically. We are not going to use any manual jumpers like in the case of my ISA or EISA. Whenever you are going to insert a particular card into the PCA slot, you're going to allocate a particular configuration space, and in this particular configuration space you're going to get all this particular um, things configured. And why it is mattered, so basically in the case of ISA we have already seen that every interrupt, DMA channel, and input output address was set by hand via the jumpers or DPS switches. And in the case of my EISA, it was improved with software setup, but still it is manual and error prone. And in the case of my PCI, I'm going to use my BIOS and OS, which is going to enumerate my configuration space at the boot time itself. So whenever the system is booting, it is going to basically configure the space, and it is going to auto assign all the particular resources. I don't need to manually allocate it. And this particular automatic process is known as plug and play model. And the major problem which we were facing in the case of my ISA or EISA was interrupt sharing and bus bridges. So basically, I was having a shade level triggered interrupts in the case of my ISA, but PCI's INTA and INTD lines can be shared by multiple devices. I can have multiple devices sharing the same interrupt lines, unlike your ISA edge triggered lines, where each card were using a separate dedicated IRQ line, which was basically running out of resources when your number of cards are being increased. And we are going to have PCA bridges and hierarchies. So basically, a bridge is nothing but it's kind of a connection between the CPU memory to one or more segments of PCA, and we are going to have PCA to PCA bridges, which using this we can basically increase the number of slots per segment. So that is PCA bridges were introduced in our PCA, which were lagging in our ISA and EISA. So coming to the comparison, if I want to compare between ISA, EISA, and PCA, so ISA was introduced in 1981, and EISA and PCA was introduced later. And data width in the case of my ISA was 8 to 16 bit, whereas in the case of EISA was having 32 bit, and PCA also 32 bit, and it can be extended to 64 bit. And the bus clock was 8 megahertz, and it is CPU tied. Whatever the ISA bus we were using, it is basically CPU tied. Whereas in the case of EISA, it is 8.33 megahertz. And in the case of my PCI, the bus clock is independent of CPU. So whatever the clock frequency we are going to have, whatever the clock we are going to have in our PCA bus, which is basically independent of CPU. And maximum throughput is 8 megabits per second in the case of ISA, whereas in the case of EISA, it is 33 megabits per second, and PCA it is around 133 to 533 megabits per second. And there is no plug and play in the case of ISA, whereas in the case of EISA, it is very limited, and in the case of PCA, we have the option of plug and play. And bus mastering is very, very limited in the case of my ISA, but it was very complex in the case of EISA, whereas in the case of PCI, it is native and standardized. That means any particular peripheral can act as a bus master. And coming to the advantages of PCI, it is going to have higher bandwidth and it is processor independent. It can use x86 processor, PowerPC, and Spark. And whereas we have plug and play model and configuration space, native bus mastering, shared interrupts, and smaller connector, and open license and scales via PCA to PCA bridges. And disadvantages, we have shared bandwidth. More cards means less per card. We are going to have less bandwidth if we are going to have more cards, and we are going to only have 4 to 5 slots per segment, and we have something known as electrical limit. We are going to anyways discuss this particular point in our upcoming sessions, and it is half duplex. PCI is half duplex. That means it cannot send and receive simultaneously. Any one operation should be done at a particular time. And clock speed, if it is going to, it is restricted to 66 megahertz due to something known as signal integrity. This is also we are going to discuss in our upcoming sessions. What is happening? Why we can't increase the clock speed? And it is going to have 5 volts or 3.3 volts or universal keying fragmentation, and it's a still parallel bus shade bus topology. PCA is also a parallel bus topology. What is going to happen if we are going to use parallel bus topology? Also, we are going to discuss in our upcoming sessions, and it is also going to have arbitration complexities when we are going to have multiple bus masters. Arbitration becomes very difficult. So these are the disadvantages of PCA. And the new terminologies which was introduced in PCI is multiplexer addressed data lines, configuration space, PCI SIG. So basically, SIG is nothing but special interest group. So basically, the vendor neutral special interest group that owns and evolves PCI specifications. And ISA had no formal governing body, and EISA was driven by a smaller vendor consortium. Whereas in the case of my PCA, PCA was having a special interest group and it is vendor neutral. No vendor is going to control it. And we have something known as plug and play model. We have already seen this particular terminology. And burst transfer mode, this is one terminology. And shade level triggered interrupts also we have seen in our previous slides. And universal keyed cards, like you can basically have any particular universal cards that can be uh, inserted into it. And PCA bridge, this is the new term which we have discussed in our particular session. And this was evaluation of our PCA, where we are basically seeing this in our particular session. And next we are going to have PCA X and PCA Express. So we are basically in our next session we are going to in detail discuss about what was the disadvantages in our PCA. Then we are going to discuss about PCA X and PCA Express. So this was about this particular session, and where we have discussed about introduction to PCA, advantages of PCA over ISA and EISA, and little bit disadvantages of PCA. And we are going to discuss more in detail disadvantages of PCA, which we were having in the case of PCA. And that's the reason we are going to discuss PCX and PCA Express. What are the reasons which we are going to learn PCX and PCA Express apart from PCA? That is what we are going to discuss in our upcoming sessions. So if you like this video, please like, share, and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.